All right, Gen Chem, welcome to another installment of Kinetic Molecular Theory. This time we are going to be talking about the speed of particles and how they're moving. We're also going to be talking about diffusion and effusion. We're going to be talking about phase changes. And one of the phase changes that we're really going to be focusing on is boiling point, because boiling point really has a couple of different things that go into it to really make something effectively boil. So let's talk about the movement of these two trucks. So I have a question for you. If I'm going to compare the mass and the speed of these two trucks, is it possible for me to get these two trucks to have the same amount of force? Now, if you've taken physics before, you know that force is equal to the mass of that object multiplied by the acceleration of that object. The mass of this monster truck is probably about 4 tons, and the mass of this toy truck is probably about a pound, maybe a pound and a half. Is it possible for me to get the force of those two trucks to be the same? It is. Now, I would have to have this small truck going really fast. And that would have to be accelerating tremendously fast. But if this large truck was going really, really slow, like maybe a millimeter an hour, I could have it being the same force as that small little truck. So let's think about this in terms of gas molecules really quick. So kinetic energy is also a matter of force. And in physics, the equation for kinetic energy is 1/2 of the mass of the object multiplied by the velocity squared. Velocity is just a fancy word for speed, how fast something is traveling. So think about this. The average kinetic energy of all gas molecules at the same temperature are the same. So the average temperature equals the same average kinetic energy, whether that molecule is really big or really small. So think about that monster truck versus that smaller truck. So if the energy is the same for really big molecules as it is for small little molecules at the same temperature, what does that mean about the speed or the velocity of those different mass molecules? It means the velocities have to be very different to have the same amount of energy. It means the really big molecules are traveling really slow. And it means the really small molecules are traveling really fast so that they have the same kinetic energy. Okay? All right, so let's think about this then. Which type of molecule would move faster at a particular temperature? So if they were all at the same temperature, would I have light molecules like hydrogen move faster, or heavy molecules like sulfur hexafluoride? Think about what we just said with the monster trucks. Yes, lighter molecules move faster at the same temperature. So lighter molecules move faster at the same temperature. Okay, so question. We need to now define diffusion. And I'm sure you've all experienced diffusion. If you've ever been in a room where somebody has sprayed cologne or perfume, and pretty soon, even in the back corner of the room, you can smell that perfume or that cologne, you have experienced diffusion. Diffusion, I want to get out the real definition here so I don't mess up. It's the movement of a substance from an area of high concentration to an area of low concentration. So it's the movement of a substance from an area of high concentration to an area of low concentration. Does that sound like something you maybe learned about in biology last year? Does that sound a lot like osmosis? Osmosis is just a form of diffusion, but it's a form of diffusion through that semi-permeable membrane. Okay? So notice I have to have the flow of substances through another substance for it to diffuse. So substances can only diffuse in liquids and gases. So this only happens in liquids and gases because I need the ability of the molecules to be able to flow with each other. Okay? So can we think about diffusion in terms of these molecules? If I have fast molecules, which are light molecules, traveling faster than the heavier, slower molecules, what kind of things, if I release them out into the air, do you think you'd smell first? Things like motor oil that are heavy molecules, or things like ammonia that are really light molecules? You'd smell that ammonia first because it would diffuse faster and it would reach your nose faster. Okay, so remember that light molecules are smaller molecular weight, smaller molar mass molecules diffuse faster than heavier molecules. Okay, so let's talk about change of state. We have lots of different changes of state here. So change of state really just means what phase or what state are these molecules in? Are they in the liquid phase, solid phase, gas phase? Can I get them to change back and forth between these states? I sure can. Okay, so, and there goes my thing again. Okay, let me see if I can get us back to the correct page. I don't know why this keeps on jumping around. It will probably jump again. Okay. So here's a diagram of what a gas would kind of look like. Yep. Here we go again. Okay, back to where we were. Diagram of what a gas would look like and what a liquid would look like. Now look at the molecules in the gas. Lots of space in between them. The gas takes up pretty much the whole volume of the container. The liquid, notice it does not take up the whole volume of the container, and there's very little space in between the molecules. Okay, so in a given sample of a liquid at a given temperature, the average kinetic energy of all those molecules is constant. Okay, so if all these molecules all averaged out, the average of these molecules, so the average kinetic energy of all those molecules would be constant. Constant. Okay, it doesn't change. Okay, but just like if I give you all a test, I can get a class average of a test. But does that mean that every student in the class got that same score? No. The actual individual kinetic energy varies greatly. I have students that get 100% on the tests, and I have students that don't perform very well on the tests, and everything in between. So individual scores, just like the kinetic energy, can vary greatly. So the actual individual kinetic energy varies greatly. Okay, so let's think about taking those individual molecules and what it takes to actually get them to evaporate from a liquid to a gas here. Okay, so in order for a molecule of a liquid to evaporate, and when I say evaporate, we are just going from the liquid state to the gas state without being at the boiling point. So this is going from the liquid state to the gas state without being at the boiling point. Okay? So there are two things that a molecule needs to have in order for it to vaporize or evaporate. Okay? So the very first thing that a molecule has to have in order for it to be successful in changing from the liquid state to the gas state is it needs to be on the surface. The molecule, or we could say particle, needs to be on the surface of the liquid. If that molecule or that particle is deep in the middle of a drop or a cup or something of that liquid, there's no way it's going to be able to vaporize because it's not going to be able to get out of that liquid to become a gas molecule. Okay? There's one more thing that it also needs. It needs to have enough kinetic energy to break free of the molecular forces of the neighboring molecules. Remember a while back when we talked about intermolecular forces? And we talked about three different types of intermolecular forces. We talked about London dispersion forces. We talked about dipole, and we talked about hydrogen bonding or hydrogen bonds. Those forces make a difference on whether a molecule can leave that liquid phase or not. The stronger the intermolecular forces, the harder it is for those molecules to break free of the neighbors. It's kind of like when you were a kid and you played Red Rover, and you had to break through the arms of the kids that were calling you over. Hopefully you didn't play that. It leads to a lot of broken arms. But if you ever played that, you knew that the kids that had the stronger forces, it was hard to break free through those hands. Okay? So the second thing that we need is we have to have enough kinetic energy, and I always shorten kinetic energy to Ke, to break the intermolecular forces. Intermolecular forces, or the IMFs, of the neighboring molecules or particles. Okay, so I've got to be on the surface, and I've got to have enough kinetic energy to break those neighboring molecules, IMFs, intermolecular forces. Okay, think about this. If I'm going to look at the blue line, that's T1, and only a certain amount of molecules in a group will actually have enough kinetic energy to do that, to break free of those intermolecular forces. So if I'm at T1, and this is my average temperature at T1, that's my average temperature. Notice I only have this many molecules that actually have enough kinetic energy to break free of those intermolecular forces and become vapor. Okay? But if I raise the temperature, it shifts that average up here. So this would be my T2 average. and X bar just means average in statistics and in science. Notice if I shift that, notice what happens to the number of molecules that actually have enough kinetic energy. I have more molecules that have enough kinetic energy to break free. So that tells us the more that we shift the temperature up, the more molecules that we will have that have enough kinetic energy to break free of those neighbor IMFs and become vapor. So think about this. Only a certain number of molecules actually have enough kinetic energy to escape the attractive forces of their neighboring molecules and evaporate. Okay? Yet, if I have a drop of water on a counter, if I put a drop of water on a counter and just let it go, in 10, 20 minutes, that drop of water is gone. How does that happen if the average temperature stays the same? If all these molecules leave, doesn't that leave the high kinetic energy molecules out and it lowers the kinetic energy of that drop? It doesn't. Why? Where does the extra energy come to keep the average kinetic energy the same? How do these other molecules acquire the needed energy to evaporate? Where does that energy come from? Let's think about that. Think about what happens when you hop out of a swimming pool on a hot day. When you first hop out of that swimming pool, even if it's a hot day, like 95, 100 degrees, you're cold. Why do you feel cold? And there goes the bell. You're going to say you feel cold because the water is evaporating from you. Doesn't it take energy to evaporate? Yes, it does. So that energy that it takes to evaporate is the water is taking it from your body. That's why your body feels cold, because it's cool. It's taking the energy from your body. So that's why you feel cold. Okay? So the energy comes from the surrounding materials. That's why if you've ever touched a table right after it's been wiped off with a wet rag, that table's going to feel cold, because to have that water from a wet rag evaporate off the table, it took the energy from the table to do that. So the table is now cold because it comes from the surrounding materials. Okay, so is it possible, let's think about this, is it possible for a gaseous particle that has evaporated to collide with the surface of the liquid that it just left? Yeah, it is. And if that particle has low enough kinetic energy at this time of that collision, could that particle again join the water or the liquid and condense? Yeah. Okay, it may become part of the liquid. However, if it comes from a container that is open, there's very little chance of that particle actually finding its way back into the container. But if that container is closed, say I have a jar with a lid, okay, or a bottle with a lid, that chance of that type of collision is greatly increased. In fact, a point is reached where just as many molecules of gas are returning to the liquid state as molecules of the liquid going to the gas state. Okay? So in a closed container, the rate at which molecules evaporate equals the rate at which they condense. So in other words, if I have this reaction where X liquid is going to X being a gas, notice I have an arrow that is going back and forth. The rate of the liquid going to the gas is equal to the rate of the gas going to the liquid. Okay? And that's why things stay when they're bottled up. Okay? That is what we call equilibrium. Now, equilibrium just means the rate of the forward reaction is the same as the rate of the reverse reaction. The molecules are indeed changing. They are going back and forth between the liquid and the gas stage, but the rate that they're changing is the same. So that means the net change, or the overall change of that system, is zero. Okay? So we say that this is an equilibrium condition. Okay? It's a special kind of equilibrium called a dynamic equilibrium. And it's dynamic because notice here in this equilibrium picture, I have molecules that are still changing. I have the red ones that are going to the vapor stage, and I have the blue ones that are going to the liquid stage. But the rate is the same, so the net change is zero. The net change is zero, even though the individual molecules are still changing back and forth. That is dynamic equilibrium. Okay, let's talk about boiling point for a second. Okay, the phenomenon of boiling, we've all seen water boil on the stove, involves the fact that bubbles of water vapor, okay, so those bubbles of boiling water are actually bubbles of water, form anywhere in the liquid, and they can rise to that surface. This only occurs if the vapor pressure of the liquid is equal to the atmospheric pressure. Okay, so the pressure of the molecules from the liquid going to the vapor state, pushing up out of that liquid, has to equal the pressure of all the atmosphere pushing down on it. Only when the vapor pressure, or the pressure of the liquid molecules turning to the vapor, equals the atmospheric pressure, can that liquid actually boil. Okay? It is possible to boil water at a temperature less than 100 degrees, though. I just have to lower the atmospheric pressure, or the pressure around that liquid. Okay, so what's the approximate boiling point of water on a typical day in Salt Lake City? Okay, normal boiling point is 100 degrees Celsius. Now, normal means normal pressure. Which the scientific community has said is sea level. Right? We don't live at sea level. Okay? Or we could say it's also 1 atmosphere. Another standard measurement is 760 millimeters of mercury, or 101.325 kilopascals. Or at the English system, I think it's 14.7 psi, pounds per square inch. There's lots of different ways that we measure pressure in the scientific community. In chemistry, we really use these 3 things mostly. Okay? So, is it possible for me to boil water at less than 1 atmosphere? Yeah, I just have to lower the pressure, because lower pressure means I have to have a lower vapor pressure, which means a lower temperature, right? So here in Salt Lake City, we are normally at 645 millimeters of mercury. If you notice, that's the standard 760, or 86 kilopascals instead of 101. So we're lower. So does that lower our boiling point? It does. It lowers our boiling point here in Salt Lake City to about 98 degrees Celsius, about 2 degrees less. Okay? So that means that if I go even higher, my boiling point goes even lower because I have less atmospheric pressure. So here we go. At sea level, at 1 atmosphere, my boiling point would be 100 degrees. But if I go to Pikes Peak, which is the tallest peak in Colorado, it goes down to about 85 degrees Celsius because we're at about 4,400 meters. Here in Salt Lake, we are at about 1,500 meters. So Pikes Peak is about 3 times higher than we are here. But if I go up to Mount Everest, which is at about 8,800 meters, it goes all the way down to 71 degrees Celsius. Okay? So, it's also possible for water to boil at temperatures higher than 100. I just need to raise the pressure on there. If the pressure above the water is in excess of 1 atmosphere or 760 millimeters of mercury, a greater amount of energy is going to be needed to get that vapor pressure even higher, to push those molecules apart and allow them to vaporize. Okay? It's also important to note that different liquids have different boiling points. Liquids with low boiling points have low intermolecular attractions for each other. Okay? So liquids with low boiling points have particles with low IMFs, or intermolecular forces attracting each other. Okay? So when they only have London dispersion forces, they're going to have relatively low boiling points. Substances evaporate more rapidly because they have low IMFs, are said to be volatile. Okay? Liquids that boil at high temperatures have high IMFs. They have high intermolecular forces, and they have, or intermolecular attraction, and they are considered non-volatile. Okay? So you can see this. If I poured out a bottle of acetone, which is nail polish remover, and I poured out a bottle of oil, car oil, engine oil, which would you expect to be around for a long time if I poured it out on the driveway? The engine oil would probably stay there for years. I would have to get there and sit there and scrub it off because those molecules are really big and they have high intermolecular forces. Acetone, those molecules are really small and there's not a lot of intermolecular forces. So the acetone will diffuse and evaporate much quicker because it is volatile and it doesn't have a lot of intermolecular forces. Okay, I want to define sublimation. So sublimation is where we go straight from the solid to the gas state without going through the liquid state first. So a change from the solid state to the liquid state or phase without going through the liquid, it's change from the solid stage. Oh my, I can't think right now. As a change from the solid state to the gas state without going through the liquid state. Okay, so I'm going straight from solid to gas. So a good example of this would be dry ice, which is just carbon dioxide in the solid state going to carbon dioxide in the gas state. And you've all probably seen dry ice. Okay, so dry ice is one thing that sublimes. Another thing that sublimes is iodine. Iodine solid will go to iodine gas and make this really pretty purple cloud. Okay? Melting point. Melting point is where we go from the solid state to the liquid state. So solid state or phase to the liquid phase. And yes, my computer is freezing. Hopefully it won't freeze for too long. Okay, so melting point is solid phase to the liquid phase. So this next thing, how are melting point and freezing points related? Aren't they the same thing? Melting is just going from the solid phase to the liquid phase, and freezing is just going from the liquid to the solid phase. It's the same thing, only you're approaching it from the different ends. So melting point is solid state or phase to the liquid phase. And then freezing is liquid to the solid. They're the same thing, only starting at opposite ends. All right, so that's enough for today. We will talk about phase diagrams and energy diagrams next time, and we will wrap up our kinetic molecular theory chapter next video. All right, see you later. Bye.